Hi and welcome back. This is video 2 of 3 for Chapter 5. Now, Chapter 5 itself gets us in the mindset of talking about um, electricity. Now, in the previous video, I talked about the electrical force, and I mentioned that it was a fundamental force, a little bit like gravity. In this video, we're going to talk about the electric field and its relationship to the electric force, but primarily about the field itself. And that's because in many situations, the field is far more useful to us to talk about than the force is. So, that said, there are two basic types of what we call distributions of charge. By distribution, I just mean an arrangement of charges sitting out somewhere that ultimately we want to look at the electric field due to. The two basic types are discrete and continuous. So these are charge distributions. Now, in truth, they're all discrete because, as we mentioned last time, there is a atom of charge, which means that ultimately you could think of something as being continuous, but in truth, it's just made up of little pieces. Now, that said, if you remember what the Coulomb force looks like, you have 1 over 4 pi epsilon naught Q1 Q2 R12 over R12 squared. Now, in general, we are interested in the force on one charge due to the electric field of another. And the reason for that is because if you remember the previous video, we talked about some of the properties of the electrical force. And one of the properties was that it was able to act on things at a distance without a clear connection. So in that type of methodology, what we say is that the presence of charge, we'll call this Q2, creates some sort of electric field. So maybe this is an electric field or something like that, pointing around in space. It's a vector. And when you take another charge, we'll call Q1, and place it in the presence of this electric field, it's the interaction between this one's electric field and this one's electric field that creates the force. Okay? So, under this model, we're able to explain why it is that you have this action at a distance. And we use the same methodology when we talk about the gravitational field at higher levels. So, let's pretend we're talking about the force on Q1 due to Q2. If I were to look at this equation right here and call this the force on 1, then everything that doesn't explicitly deal with Q1 belongs to Q2. So what we say is that this right here belongs to Q2. Now you would write this the following way. The force that Q1 feels is a consequence of placing Q1 in the presence of the electric field due to Q2. Now, we're interested in what the electric field looks like at one's location. Now, this right here is typically the way we define the electric field. For example, E2 here would be equal to F1 divided by the charge. Okay? But if you look at this a little bit more closely, we have an analytic way of writing this, and that is that E2, or just E in general, the electric field in general due to a point charge, that is a charge that has no real substance to it other than the fact that it has charge and perhaps mass, would be this: Q R hat over R squared. Okay? Now this right here is typically what we start with when we talk about electric fields. Now, when you have a distribution of charge, that is a bunch of charges sitting around in space, then you can talk about the net, that is the total electric field at a location in space. But before we get to that, what I'd like to do is to draw you what the electric field looks like due to a point charge, both a positive charge and a negative charge. So let me draw a coordinate system here, and what I'm going to do is I'm going to place the charge at the center. So here's our coordinate system. Maybe this is the y-axis, maybe this is the x-axis, the z would be in and out of the page. And at the center right here, I'm going to place my charge q. Now, the electric field is what's called a vector field. That means that it has magnitude and direction, but it's not like the vectors that we're familiar with. Most of the vectors that we've dealt with up to this point are single lines that point from one, they have an end for a tail and a head, and they point a direction, and they have a magnitude. Well, fields are not one vector, but literally an infinite number of vectors. Typically, at least in the case of the electric field, they originate from one point or one set of points in space, and the tip terminates into another point or another set of points in space, depending upon what the configuration of charge looks like. But for a single charge, the way we would draw the electric field would be like this. If it is a positive charge, it radiates outwards like this. Now, truthfully, there would be an infinite number of these little vector lines, but that would take an awful lot of time to draw, since it would be infinite. So I'm just going to draw a few of them, like this, okay? Now, here's the deal. In this case, our charge is positive, and these vector, their tails sit at the location of the charge. If you want to think of it, they are originating from this charge. They come out of the charge. So as a consequence, we say that positive charges are the source of electric fields. Now, I want to be very clear what I mean by the source. In this case, many times we view fields almost as though it's, we'll say, a lake of water, okay, or a river. So the water itself would be the field, but we know that the river has a source somewhere, a head, a place where that water comes from. And that's sort of what we mean here. When we say the source, we mean that this right here would be where the field comes out of. Okay? Now, that said, if I were to look at a negative charge, which I'll place here, so here's my charge here again at the origin, but this time it's negative. In this case, the field lines look almost identical to what we see here, except instead of coming out of the charge, they go into the charge. I'm just going to draw a few of them. Like this. Now be clear, or rather to be clear, there are literally an infinite number of these things. But we're just drawing a few of them here. Okay? So, in this case, what we say is that negative charges are at the sink of electric fields. So to go back to the water terminology, I want you to imagine, say, doing dishes in your kitchen or something like that. And when you turn the faucet on, the faucet is the source of the water. That's going into. What's it going into? Oh, the sink. The sink is where the water ends up, okay? And that includes the drain. So sources and sinks, like I said, typically are the terminology that we use when we talk about these things. The positive electric charge is the source of the electric field, and the negative electric charge is the sink. Now, it turns out that when you have charges that are within reach of each other like this, they're in approximately the same region, that you can take and you can look at what the overall field might look like. Now, why overall? Well, this is a vector field. These are vectors, and we know, like for example, when we talked about forces, that ultimately, you're usually not interested in just one force. You're interested in all of the forces that are acting on something. That is the net force. And that's how it is here for electrical stuff. We're interested in the net electric field at a given point in space. So imagine that you have your positive charge here. So here's your positive Q. And then you have, maybe your negative charge here. And here's your negative Q. So I'll put Q minus there, Q plus there. It's just pluses and minuses to remind us. Now, so were you to draw, and I'll tell you what, I'm going to use colors here just because it's going to make my life a little bit easier. I'll use purple for positive, and we'll dot these lines like this. So if I were to draw that right there as being my just one field line of the electric field coming from the positive one, radiating outwards like this. And I'm going to use, we'll say red for negative. And that would be about, let's see here, 1, 2, 3, 4, 5, 2, 3, 5 about here. So there's my negative right there going in. Now what I want to do is I want to look right here. I want to look and see what's going on right there. And I'm going to take, and let's see, is it possible for me to copy and paste that? I don't think so. So let me just sort of, I'm going to box this. Whoops. No, that's fine. We'll use that. So let me just box this region. I want to sort of blow this up and look and see what's going on there. Okay, so here if you were to zoom in, specifically at this point in space, this is where we're interested in the electric field at. At this point in space, if you look, you have the negative electric field going down like this, and you have the positive electric field going up like this. Now, if you were to look at the angles here, what you would discover is that this angle right here and this angle right here are the same, which means that if I were to sort of split this in half, these angles are going to be the same right here, okay? Because you have, two straight lines, intersecting each other, and et cetera, and so on. So, so here, at that point, here's that point, you have the positive electric field going up like that, and you have the negative electric field going down like this, like that. Okay, I'm going to cut this in half like this. Oops. Let's go with the line. So I'm cutting it in half like that. Now, so let's pretend, just for the sake of argument, that these both have the same magnitude, the same value. So maybe this has like 1.6 times 10 to the minus 19th coulombs of charge. And this is negative 1.6 times 10 to the minus 19th coulombs of charge. Well, if you look at the form of the equation right here for the electric field, what that means is at that point in space, because of the symmetry that we've chosen, the electric field is going to have the same magnitude due to both of these. So the magnitude of the positive one and the magnitude of the negative one are going to be the same at this point. It's the directions that are different. Now, also, because of the symmetry that we've chosen, and this is the center line. This is the center line between these two charges. What you'll see here is that the up part here of the positive electric field and the down part here of the negative electric field have the same length. They have the same magnitudes. And so what that means, because they have the same angles here, is that they're going to cancel each other out, just like forces. Now what's left is a side part of this and a side part of this that both point down the positive x direction. And if I were to look on a line right here, centered between these, like that, at that point in space, looking at the electric field, you would have cancellations just like this happen, and the net electric field would point like this on that line. Okay, now let's pretend that you did exactly this for lots and lots of locations here. And the goal here was to find the magnitude and the direction of the field and to get a sense as to what the overall net field looks like. Okay, so let's pretend we're doing that. And actually what I'm going to do, just to save some time for us, is to go back over here and let me just snag my electric fields, my charges. A little copy. We'll do a little bit of pasting action right here, like this. Okay. Now let me erase this just a little bit. Looks like I lost my x-axis over here. That's okay. That still makes it a little bit easier. So here you have your x-axis, and let's not forget that this one right here, this is the negative charge and this is the positive charge. So like I said, if you were to plot these field lines, what you would notice would be at the very center along the x-axis, and let me just go ahead and put x there to be sort of pedantic about this. So this is the x-axis. So what you would notice is that there would be an electric field that looks like it pointed from Q positive straight into Q negative. So it points from the source into the sink. Okay. Now let's pretend that you plot these things, and I'm going to try to freehand this. There's a picture in your book that you can look at. What you would see is that your electric field, your net electric field, when you add this thing up, okay, is going to have field lines that point from the positive charge that go into the negative charge like this. All right. That's kind of hard to freehand. That's not too bad. See if I can connect them. These styluses are hard to use, so this one's going to be a little more complicated because he's sort of going out of the sheet, but he follows through this way, and then he comes back in over here like that. This one right here basically is going to look like this. Like that. And then at the ends here, you'd have a positive one going that way and a negative one going into this. Okay, so this is what the net field is going to look like. All right. Now this particular shape, because we have two charges that are separated by a distance, this is called a dipole. And we mentioned this, last video, but this particular configuration itself is called a dipole. Okay. So that said, let's keep on keeping on here. And let's talk more about charge distributions. Okay. So we had another page here. So like I said, that there are discrete charge distributions and that there are continuous charge distributions. So with a discrete charge distribution, I want you to imagine, we'll say a couple of charges sitting around here in space like this. Q1, Q2, Q3, Q4, Q5, and maybe Q6. And, maybe over here is my coordinate system, the center of my coordinate system, like this. So what I have here are a bunch of vectors. So I'd have, R1 locating where Q1 is. R2 is there. R3 is there. R4 is there. R5 is there. And R6 is here. Okay, so there are my vectors locating with respect to the origin of my coordinate system all of my different charges. R1 vector, R2 vector, R3 vector, R4 vector, R5 vector, and R6 vector. Well, let's pretend that I was interested at the, in the location of, the electric field at this point in space. So I want to find out what it looks like there, and I'm going to use a different color just to sort of point this out here. I'll use blue again, or purple, whatever that is. So this right here is R. This is my R vector. And this is the point in space where I want to find out what the electric field looks like due to all of these charges that are sitting around. Well, okay, so let's just think about one of the charges. I'll look at Q1. So, for example, if I were looking at Q1, this right here would be the origin of my coordinate system. Okay? Q1 sits maybe somewhere over here. The point in space that I'm interested in, sits over here somewhere. So this right here is R1. This right here is R. And the electric field here is due to this charge right here, putting the field there. So this right here, and I want to put this as a dotted line, is how far away this charge is from this location in space, and also the direction. Now, in terms of vectors, if you were to think of adding things together, this is being R1, this is being some unknown vector, this vector plus this vector is going to equal to this vector. Okay? So, R1 plus some vector I'm going to call question mark is equal to R, just through simple graphical vector addition. Okay? So, this vector right here, if you solve for it, would look like R minus R1. So this right here is R minus R1. That's the distance and the direction. Okay, that's what that vector represents. So now if I go back and I look at my equation for the electric field right here, and I'm just going to snag this and copy it, and then paste it right here. It's this vector right here that goes into this. And it's the direction right here. This right here is the direction of R hat 1, whatever that is. This would be R hat 1. Points from here in that direction. This is that right there. Okay? So graphically, the way we would typically write this is that my electric field at location R, right there, okay, location R, is equal to 1 over 4 pi epsilon naught. So there's that. There's our charge Q. In the denominator, we have R squared. Now, R squared is really this right here. It's how far away this thing is from. Okay? So R squared would be the length of R minus R1 squared. R1 here, R1 hat, the unit vector, is R minus R1. That's the direction it points in. But to make it to have a length of 1, we divide it by its length. Okay? You put that into here for r hat. And let me just sort of, I'm going to call this just r1 for right now. And let me rewrite this just to make some room here. 1 over 4 pi epsilon naught q over, this now becomes r minus r prime, or r1 cubed. And what's left is your vector r minus r1. So this is how we would take and actually write the electric field due to charge 1 at that location in space. But so if you look at this, the only real change between E1 and E2 and E3 and E4 and E5 and all these other things would be the value of charge that they have. In this case, it's 1. We don't know what the others are. Okay, would be the value of the charge that it has and where it's located relative to R. Okay, so E2, for example, would look almost identical to E1. The change here would be 1 over 4 pi epsilon naught. That's the same. Now it's Q2. Now our location vector is R minus R2. And in the denominator, we have R minus R2 cubed. Okay? So you can imagine if I wanted to find out what the total electric field here was, the total, which I'm just going to call E, at location R, would be what you get when you add up all of your charges, in this case from 1 to 6. It's all of the electric fields at that location. Okay? Or if you went ahead and sort of put in a generalized expression for this, it would be 1 over 4 pi epsilon naught, the sum of, from 1 to 6, of q sub I, r minus r sub I, divided by r minus r sub I cubed. Now, this is typically how we write discrete charge distributions. This is this electric field. The thing is that if you have large numbers of charges, you can take and you can turn this sum into an integral, which is something that you do pretty regularly whenever you're doing, calculus. So what we do is to differentiate between the different types of of continuous charges. And so there are 3 basic continuous charge distributions. You have one that is along a line or a curve. So it would be one-dimensional. You just have a bunch of charges lined up along a line that are so close together that you can think of them sort of as continuous, rather. So in this case, instead of talking about charge directly, we talk about charge density. And charge density, here we use the Greek letter lambda for it. And it is the total amount of charge that you have sitting along how long that line is. So it's coulombs per meter. Okay? You can also have your charge sitting on a surface, like draped across a sheet of material or something like that. So along a surface. This is 2D. Here, we use rho to denote surface charge. And that would be charge per area, or coulombs per square meter. The last one, and arguably the most useful one, although we're not going to be using it a whole lot in this class because of the level of calculus that's involved, would be charge that sits in a volume. This, of course, is 3D. We use rho for charge density in this case, and it is charge per volume, or coulombs per cubic meter. Okay? So here are your three basic charge distributions from a continuous standpoint. Now, if you look at my equation here for the electric field, it depends upon knowing the amount of charge, Q. The way you make the jump from a discrete charge distribution to a continuous one is to take your Q and to put in whatever charge density it is you're looking at. Say, let's pretend that it's along a line, and we'll say it's along the x direction, lambda times dx. And what that does is to allow us to take our field as a sum and turn it into a differential field. And then we can integrate, and that gives us the total electric field of the point in space. So, for example, along a line or a curve, this might look like, so on a line or a curve, your differential field when you write it would be dE of r is equal to 1 over 4 pi epsilon naught. So that's still there. Now up here, this really is differential charge. A small amount of charge along the line would be equal to whatever the line charge density is times a little bit of the line. So you would write that as dq prime, because we're going to be integrating over the location of the charge. R minus R prime divided by R minus R prime. That's the length of the vector cubed. Now when you integrate this, when you integrate both sides, this would become E of R on the left-hand side. And on the right-hand side, you have 1 over 4 pi epsilon naught, the integral over whatever the length of your charge is, the curve or whatever it is, lambda dx prime. We'll assume that, actually let's not assume x, let's not assume anything like that. I'm just going to call it L prime, over the length, R minus R prime, divided by R minus R prime cubed. So that's on a line. Now, what about along a surface or in a volume? Well, it's really no different, except now you're integrating over areas or you're integrating over volumes. So on a surface, your electric field would look like 1 over 4 pi epsilon naught. Now you're doing a double integral. This time it would be over an area. I'm just going to acknowledge the fact that it's a double integral. And surfaces use 2D charge densities. So that would be sigma dA prime R minus R prime divided by the length of R minus R prime cubed. Now, in a volume, E of R looks like 1 over 4 pi epsilon naught. Now we're doing a triple integral, 1 over volume, rho dV prime R minus R prime over R minus R prime cubed. So as you can see, there's really no difference between these other than the fact that we're dealing with a line here, an area here, and a volume here. Now, to finish this off, at least with respect to what these look like, if you're looking at discrete charges. Our electric field looks like something we already know. 1 over 4 pi epsilon naught, the sum of I going from 1 to however many charges we have, q sub I, r minus r sub I prime, divided by r minus r sub I prime cubed. So as you can see the jump from the sum to a continuous thing like this. Now, as we're going to discover, being able to do these integrals is useful to us, but primarily what we're going to be interested in is the end result of the integration. And I'm going to save that for video 3. So in this case, what I'd like to know is what the electric field is where the electron sits in the lowest orbital position of the hydrogen atom. Now, we did an example sort of like this in previous video, dealing with the force, at that point. But what I want to do, like I said, is just one that deals with, what the field looks like there. Now, in this case, we don't care that the electron is here. We just care that that's its position. We don't care about its charge or anything like that. So what we're given here is that the distance from the origin to where the electron would be is 52 picometers. Now, a picometer is very small. I want to say, if I remember correctly off the top of my head, it's 10 to the minus 12th. Let me verify that. Yep, 10 to the minus 12th. So this would be the same thing as 52 times 10 to the minus 12th meters. The thing that's producing the electric field is the proton. Its charge is 1.6 times 10 to the minus 19th coulombs. Okay? Now what we're trying to find here, got vectors on my mind, is the electric field at that point in space. Okay? Now, so here's the deal. Point charges, which is what we're going to approximate a proton as, well, first, I'll tell you what. Let me write down what the electric field sort of looks like. We know it's going to be 1 over 4 pi epsilon naught q r hat over r squared. And this is, the form for a point charge's electric field. But look, this only depends upon r, that is how far away from the center you are. So if you were to draw a sphere here that had a radius of 52 picometers, centered on, of course, the proton, then the magnitude of the electric field at that point, all along the surface of that sphere, would be the same. The only thing that's going to change is the direction. Okay? So much like the gravitational field, the electric field only depends upon how far away you are from the thing that's producing the field. Okay? So it is radially symmetric. All right? So in this case, though, it's pretty easy. Our hat is, out like that, since it's centered on our charge. And here, it would be 1 over 4 pi epsilon naught. Q is 1.6 times 10 to the minus 19th coulombs. R hat, excuse me. In the denominator, it's 1.6, hilarious. It's 52 times 10 to the minus 12th meters squared. Okay. Now, so if I plug in stuff and note the fact that E naught is 8.85 times 10 to the minus 12th, I believe. Let me verify that. This is one of those constants that I personally never memorized. Let me get my little sheet here. Here we go. 8.85 times 10 to the minus 12. So this is, 8.85 times 10 to the minus 12th coulomb squared per Newton meters squared. And let me plug this into my calculator. And then get the 52 there. And I get 5.32 times 10 to the 11th. Now, let's talk about units here. In the denominator, I have a coulomb squared over Newton meters squareds. Here, I have a coulomb. I have a meter squared. What's going to happen is that this is going to flip up. You're going to lose one of the coulombs that would be at the top, right? So, or at the bottom, right? And you're going to lose the meters squareds. So this ends up being newtons per meter. Okay? So the idea here is that for every coulomb you would place, every 1 coulomb you would place here, it would experience 5.32 times 10 to the 11th newtons worth of force. Okay? Now, that said, what I'd like to also take a look at real quick is how the electric field and the force are related in a situation like this. Now, we know opposites attract and likes repel. If you look at this, Q is what could be positive or negative. Okay? So if I look at the direction here of this electric field, if I were to place a positive charge here, the force would be in the same direction as the electric field is here. Out like this. It's positive. So a positive charge would feel a force in this direction. If I were to place a negative charge, like for example an electron here, the negative charge would feel a force that is in the opposite direction as the electric field, which would be this way right here. So, one of the crucial things to pull away from this is that the force and the electric field point in the same direction, either parallel or anti-parallel, depending upon the charge that sits there. Okay? Now, let's work another example. In this case, we have 3 charges. They're all 5 microcoulombs. We know what a microcoulomb looks like. We've previously did an example dealing with those in the last video. So, excuse me. What I'd like to do is to find out what the electric field is 5 centimeters above, and specifically 5 centimeters above the center line right here. I want to find out what it looks like here. Now I'm going to call this distance right here L. And what I have here is an example of discrete charges. Okay, these are discrete charges. So, if I want to find what the net electric field is there, I want to use, if I were to look at my list of different electric field equations here, I would want to use the one that deals with discrete charges right here. So in that one, and let me just write it off here to the side. Actually, I'll tell you what, just make my life easy. I'm going to cut and paste it. This is a nice feature. So let me copy it. Copy, paste, not cut and paste. And I'm going to place it right here. And let me just, write out what I've been given here. So I'm going to call this Q1. I'm going to call this Q2. And I'm going to call this Q3. Okay? Now, Q1, Q2, and Q3 all have the same value of charge, 5 microcoulombs. It's all positive, which micro is 10 to the minus 6. Okay? Now let's talk about their distances, because if I look at this equation, I'm going to need to know how far away these things are from the origin of my coordinate system, which is right here. So if I call this one again 1, then R1, which is the location of Q1 relative to the center, is, and just to make my life easy, I'm going to call these distances D. This is D in length. This is D in length. It's 2.5 centimeters. R1 is going to be minus D x hat. R2, which is this one right here, is 0 x hat. And R3, which is this one right here, is D x hat. And D itself is 2.5 centimeters, or 0.025 meters. So there are the locations of our charges. Now, they also depend upon R. R is where our point of interest is, which is 5 centimeters above this. Like I said, I called this L. So R here lies only along the y direction. It's L y hat, keeping in mind the fact that L is 5 centimeters, or 0.05 meters. Now if I take a look at this equation right here, and I look at all of this stuff right here, it appears as though I have everything that I need. So this is what I've been given. What I want to find is this guy right here. And let's get to work. Okay? So the first thing I'd like to do is to write this out. So E of R is going to equal to, if I just go ahead and expand the sum out, 1 over 4 pi epsilon naught Q1 times R minus R1 divided by R minus R1 cubed. This is the length cubed. Now, this is going to point from here to here at that location, like this. My next term deals with R2, or Q2 rather. 1 over 4 pi epsilon naught Q2 R minus R2 divided by R minus R2 cubed. This one points from here to here. Next up, one over 4 pi epsilon naught Q3 R minus R3 over R minus R3 cubed. Now, the thing is that Q1, Q2, and Q3 are all the same. They are all equal. I'm just going to call this Q out of convenience. So Q1 is equal to Q, Q2 is equal to Q, Q3 is equal to Q. And as a consequence, at the end of the day, when I do this calculation, I'll be able to pull these things out. But if I take a look here, I notice that even though we know what R1 and R2 and R3 and R are, we have these differences in our vectors here. And what I'd like to go ahead and do here is just to sort of write those things out. So R minus R1, which would be our first one right here, is going to equal to Ly hat minus R1, which is minus D x hat. And minus times a minus, or minus times a minus is a plus. So that's what r minus r1 looks like. What about r minus r2? Well, r2 is 0. This is just r, Ly hat. What about r minus r3? Well, r3 is dx hat. So that's going to be Ly hat minus dx hat. Okay? So there are our vectors. Now let's talk about the lengths, because this is a length cube. What this really means is that I use the Pythagorean theorem to basically find out what the length of this vector is, and then I take that length and then I cube it. Okay, that's what this means. Okay, so the length here of r minus r1 is, if I look at the components here, the square root of the sum of the squares of the components, L squared plus D squared. The length of r minus r2 is just L squared. Square root of, or just L. That's how far away it is. R minus R3 is going to be the square root of L squared plus minus D squared. But when you square a negative, it becomes a positive. So at the end of the day, we can plug this stuff in, noting the fact that when you cube this, what that does is to effectively raise this right here to the 3/2 power. So this is the same thing as saying 1 over 4 pi epsilon naught. Now I'm going to call Q1, Q2, and Q3 just Q for right now. Q times r minus r1. R minus r1 is Ly hat plus dx hat. So that's this, divided by the length of r minus r1 cubed. R minus r1, the length is this. When I cube it, I get L squared plus D squared raised to the 3/2 power. So that's the first term. The second term is 1 over 4 pi epsilon naught Q, remember we're calling them Q now, times r minus r2, which is just Ly hat, divided by the length cubed, L cubed. Already you can see that you lose one of these, they get cancel. For our third and final charge, 1 over 4 pi epsilon naught, Q3 is just Q, r minus r3. R minus r3 is this, Ly hat minus dx hat. And in the denominator, again, we have r minus r3 cubed, which is going to be L squared plus D squared raised to the 3/2 power. So this right here is what our electric field looks like. But take a look. We actually have some cancellations here. For example, I have here a 1 over 4 pi epsilon naught Q positive dx hat over this. But over here, I have a minus dx hat over this. So this is actually going to cancel with that. I have two of these. These are the same thing. Okay? Now that should make sense, because if you think about the fact that they're all equal distances from each other, and we're looking at a point on the center line, then the side parts are going to cancel, and it's just going to give us the up parts. And sure enough, the side parts are the x hat direction stuff. Those cancel, giving us just the y parts. So when you, whoops, when you write this out, you get 1 over 4 pi epsilon naught q. Actually, I'll tell you what, I'm just going to write the 1 as q. I want to pull the q out of everything. I have 2 Ly hats. That's this one right here and this one right here over L squared plus D squared raised to the 3/2 power plus this right here is going to kill one of those off. A Y hat over L squared. Now, I'm going to pull the Y hat out, and then we're going to plug some numbers in. Q is 5 microcoulombs. 5 times 10 to the minus 6 coulombs, remember? We have a 4 pi epsilon naught 8.85 times 10 to the minus 12th coulomb squared per Newton meters squared. Then, let me put the Y hat there. Like I said, I'm pulling it out. Then, we have 2 times L. L, remember, is how high above this thing is. It's 5 centimeters. Okay. Divided by L squared plus D squared, which is just 2.5 centimeters. So that's raised to the 3/2 power. So that's your first term. And then your second term is just 1 over 0.05 meters squared. So let's plug this in, see what you get in your calculator. 5 times 10 to the minus 6. Let's see here. Divided by 4 times pi times 8.85 times 10 to the minus 12th. There's your term out in the front. And then, in our parenthesis, we have 2 times 0.05 divided by the square root of, actually not the square root, I take that back, divided by the 3/2 root of 0.05 squared plus 0.025 squared. You raise that to the 3/2 power. So that's that first term. And then the second term is just going to be 1 divided by 0.05 squared. And I get 4.37 times 10 to the 3/67th newtons per coulomb in the Y hat direction. So if I were to keep sig figs here, there's 1 here, there's 2 there, there's 1 there, it's just 1. So something like 4 times 10 to the 7th newtons per coulomb. So, as you can tell, the study of electricity involves a lot of factors. So you may want to go back and review that from, you know, University Physics 1. It's pretty immersive. It's generally, I'm going to be honest with you, it's generally considered to be one of the hardest areas of university physics, not because the material is complicated, but because you're seeing vectors again, and you're seeing them, and it's assumed that you already know how to do vectors and things. So go back and review all that stuff. Okay, so in our next video, what I'm going to do is I'm going to talk about continuous charge distributions. And we're going to do a couple of examples, and we're going to whip out some calculus. You may find the tools that I use to solve these things to be very useful to you if you have aspirations for a career in some sort of engineering or physics or something like that. So you're going to definitely want to pay attention, and I will see you then.